now we talk about something that might be very close to your heart, which is molecular machines, because for those who do not know, Dr. Tour is quite renowned in his work with molecular machines, specifically nanocars. And maybe Dr. Tour will tell us what a nanocar is, but he has he got the Honda Innovation Award for nanocars in 2005. The NSF Presidential Young Investigator Award, that was quite earlier in 1990. So he's been into innovation for quite long, and he has also in 2005 Tour's journal article, Directional Control in Thermally Driven Single Molecule Nanocars. Single molecule nanocars. So one molecule that behaves like a car, he's going to explain this to us, was ranked the most accessed journal article by the American Chemical Society. So, Dr. Tour, you know plenty about molecular machines. Can you tell us what's a nanocar, just to start with?
Sure. A nanocar is a single molecule car. We put in it four wheels and fully rotating axles. It has a chassis, and it can roll across a surface. They're so small we can park about 50,000 of them across the diameter of a human hair, just across the
50,000.
Yeah. So you can only see this with extremely powerful microscopes, scanning tunneling microscopes.
Do they carry cargo, or they just move?
No, they can carry cargo. We have cargo carrying ones. We've made nano trains where we hook these together and make trains.
Wow.
We've made 6-wheel versions, 2-wheel versions, 3-wheel versions, so many different models we've made. And in fact, in 2017, we won the first international nanocar race, which was held in France. And we designed the car, built the car, and then it was driven by one of my colleagues from University of Graz in Austria.
How do you drive them?
You use the electric field gradient of a scanning tunneling microscope tip. And we had to go 150 nanometers around one pylon, another pylon, and then through some posts, some end posts there. And
so you need to navigate it.
Right. And we completed the race in 1.5 hours. And the next group behind us was the Swiss team, and they came in 5 hours behind us. And none of the other international teams was able to finish the race in 30 hours. So we really excelled them all in that. And then the next nanocar race, it should have been last year, but due to COVID, hopefully it'll be next year, again in France. And but we published a paper right after the race on how to build and how to race a fast nanocar, because there's two things. You have to build it right, and you have to race it in the right way. And so we elevated the whole world. You know, scientists don't hide what we do. We elevate the world through that publication. So now the competition is going to be much harder because they've seen how we do it. And so it's just going to be more competitive now.
And since you've now explained it, it's even more fascinating. So I'm saying that nanocars are fascinating, but I have been, fascinated by those things that God has created into us that are called motor proteins. Things like kinesins and dyneins. And for the audience, those are, those, funny robots that, like have legs and move inside our cells, and they move cargo around. So, Dr. Tour, you said you needed hours to go through a racetrack of 150 nanometers. And how does that compare to the performance of a kinesin or a dynein? And I would really urge the audience, after seeing this, to go and look on the internet about what a kinesin and dynein do, and walking over those microtubules. So how does the performance of the best nanocar that you have created compare to the performance of those cars that are there in our cells?
So the kinesin, those biological ones don't really look like cars. They're much bigger than what we are. We're just a single molecule. Those kinesins are macromolecules. They're very large structures in comparison. I would say maybe more than 10,000 times larger. So we're talking at least 4 orders of magnitude larger, maybe even 5 orders of magnitude larger in length. And in molecular weight as well. So they're much smaller. Our nanocars, we've built many versions that have motors on them. They're called Feringa motors. We put them in, and these motors can spin. You shine a light on them, and the motors will spin at 3 million rotations per second, and they'll move the cars much faster than we were able to move it in the races. In the races, we couldn't use a motorized car. We had to use the electric field gradient of a tip to draw it. They wouldn't let us use our motorized cars. Our motorized cars are much faster than these other cars. So with motorized cars, we could probably complete a race like that, maybe even in a matter of minutes. How do they compare? I mean, there is no comparison. Kinesin is so much more complex. Kinesin carries huge cargoes with it. Kinesin doesn't need an external individual acting on it. What it does is it moves across a microtubule, and it moves across this microtubule by sensing the electric field gradients that are going through that microtubule, and it progresses it and carries it along to bring its cargo where it needs to bring it. Those are nature's nanomachines. They're bigger than our nanomachines, but they are so much more complex, so much more functional. They do much more work than what we are able to do, far more sophisticated. And I just stand in awe of God. He does amazing things.
So, Dr. Tour, when I just saw those videos, and the kinesin it just looks like a person. So it has those legs, and it's like having its arms like this, and it's just, grabbing on something, a vesicle or something, and it's, like moving like this, and it's walking on those microtubules. And the walking, when I just looked into the papers that describe the chemical reactions that causes it to walk, and ATP, ADP cycles, etc., and how it grabs with a microtubule, and that it has adapters, so depending on the kind of the cargo, you'll have the right kinesin, as if you have the truck that carries cement and the truck that carries glass, and it's the same truck and the same motor, but it has a different container to grab to the right cargo. And then I look into these papers that say evolution of kinesins, and what are you talking about, guys? So the question I have to you is it rational to propose that motors like this and their microtubules, and it happens that ATP is around and they use it to walk, and the cargo and the adapters, can all of this come by chance with any stretch of imagination?
Well, I think the suggestion is not that it comes by chance, but that it comes by evolution. And
yeah.
So then you have to ask the question, give me some details on that. What do you mean by evolution? How would something like this come about? How would, tell me, and they'll say, well, one small change at a time. So how many changes would it take? How many changes would it take in DNA to make a series of enzymes to build a structure that can do that? And what's the probability of being able to build a structure? How does it know to build a structure like that? There's so many mysteries. And again, to use this term evolution, just throw it out there and to feel that now stops all argument. It doesn't stop anything. It only just begs the question. Give me more detail. Nobody knows. Nobody knows. These things are so utterly complex. And what we're talking about, Ahmed, is just a single portion of the functionality of a cell that has thousands upon thousands upon thousands of portions of functionality. And how does this one portion, how does this work? Nobody knows.
Yeah, and the reason I use the word chance is that, yeah, they would say evolution and small changes, but then they say that the changes are essentially random mutation, and random is, a chance event. So from your work in motors and cars, do you put a car there and you wait for some chance to happen so that you have a better car, or maybe a car becomes a train?
No,
Is this possible at all?
that doesn't happen. Not in our lab. That doesn't happen. And it's just hard to fathom. And people will take working cells today and show their processes and somehow extrapolate this to the origin of life, and somehow extrapolate this to the functioning, the new function. So you can see, evolution is a slippery term. It's a slippery term because some people look at it in the context of making human beings. Other people look at it in the context of very small changes within a cell. There are very small changes within a cell. And if you want to call that evolution, fine. But then you have to define things for us. So what these kinesin walkers are, these are amazing new systems. We don't have examples of evolution of a new system, of a kinesin walker from something that wasn't a kinesin walker. We don't have examples of that. We don't have examples of systems changing. We have examples within a cell of small changes occurring within an organism. Small changes, but never a system level change. And this is what I'm talking about.
I noticed when I placed those kinesins back that they are in eukaryotes, which is like cells like animals and plants, but they're not there in prokaryotes, so they're not in bacteria, for example. And then I need somebody to explain to me how can the whole complete system just come out of nowhere into the first, least or the last eukaryotic common ancestor or something, which is an imaginary hypothetical creature. And there is no answer. They would just say it evolved, or it, co-evolved with something. And some people would just take this as an answer. And I had a complete debate with an evolutionary biologist, and I had this as my initial thesis. And he said, I'll bring you papers about the evolution of kinesins. And it's all the same story. The paper says nothing, says it's evolution. Puts a phylogenetic tree and says it's evolution. So
yeah,
at the point it's not small changes. Yeah.
Right. I always ask people to show me the chemistry. I can understand the chemistry. Show me the chemistry on how this happens. No black box that this goes from this to this. Show me the chemistry on how that would occur. And the explanations go away. The papers don't show the chemistry on how this thing can occur. Because the only thing they can say chemically is that you got a point mutation in DNA, and then you got another point mutation, and another point mutation. And how many point mutations are you going to need to change one system into another? And what's the probability of something like that happening without breaking the whole system, the original system? If you're going through all of these point mutations, that's the problem. It's really getting back to the heart of the chemistry of it.
So in your opinion, is the age of the Earth, for example, enough for some randomly duplicated strand of DNA to be mutated point by point into a kinesin? Do we have enough?
Yeah, it's not a matter of opinion. This has all been calculated. So if you take the universe, if you take the scientist number of the universe, 14 billion years, if you take the scientist number of the age of the Earth at 4 billion years, is that enough? And the calculations themselves say it's not enough to do all of this that would have to take place. So when you look at the improbability of all of these things happening, if you take those numbers that the scientists themselves give, the mathematics is going to lose. The mathematics wins over the evolutionary process. That wins all the time. The mathematics says no, evolution says yes. So that's the problem of what we're dealing with here. I don't use the mathematical argument because others have used that. Mathematicians have shown the real trouble with evolutionary suggestions. That's been shown for a long time, but for some reason they say that mathematicians just don't understand. So that's why I'm using my expertise, which is the chemistry, to say the chemistry is just not there either.
So let's go back to the chemistry. You mentioned you needed so many enzymes to create those creatures that walk all over the place in the cells. So my question to you is about enzymes and proteins now. Now, first, just for people to understand, can we have biochemistry without enzymes?
No.
We can.
No.
If you just put some biochemicals together, they wouldn't work. Yeah.
Life as we know it, no. If you want to say life is something else, fine. If you want to say a drone is life, silicon is life, fine. But as we know it, no. You've got to have enzymes. That's one of the critical components. That's like saying, can you have a car without wheels? I mean, it's a critical component.
And is it true that the majority of enzymes are proteins, and that we need the enzymes to create the proteins, while the enzymes themselves are proteins? Is this a true statement?
Yes.
Yeah. So I've made this. I'm sure I'm not the first one to make it. That there is a paradox there, because you cannot produce a protein from a genetic material without an enzyme like a ribosome, and they just completely neglect that the ribosome has other things other than the ribozyme. It has many proteins there, like 80 or something, from 50 to 80 or something, and they say it's RNA, and then you can. But when you look to the papers, you find that enzymes are mainly proteins, and that they manufacture proteins. So which one comes first? How do we solve this?
Right. The RNA, people will say you have a ribozyme, so the RNA itself can be an enzyme. But we have no demonstrated example of the ribozyme functioning without associated proteins. And you need to have the RNA to make the proteins. And so it's just a very difficult problem to think about how this came about. That's why I say we're clueless.
So if the second part of the question, Mike, is speculating that RNA was doing the enzyme's role rational, given what we know today?
Well, RNA, like I said, people will say that RNA can act as an enzyme, meaning that it can be a catalyst for other reactions. But it doesn't act as a catalyst without associated enzymes. So, and even if it could act as a catalyst, it's not going to be around very long. And once it breaks, and the chances of making that again are very small. People will say that RNA duplicates itself. It's only been known in primed and human-designed RNA to be very special in its design. So it's primed and ready to go. It can only duplicate 10% of itself, generally less than 10% of itself. So that's not a duplication. So this whole idea, well, RNA, once you have it, it starts duplicating itself. No, it doesn't. It might duplicate 10% of itself in the best of cases, but that doesn't do any good. And that 10% is not sufficiently long enough to act as a new duplication template.
Is it correct to say that when somebody just says a blunt statement like RNA can, autocatalytically replicate itself, that this is a dishonest statement?
Yeah, I don't know that they're dishonest, but they're uninformed.
Okay, but if the person who is saying that is, supposedly informed, if he is posing as an expert in the field, how would you describe such a statement? Is it deceiving to the audience?
Well, it's certainly misleading to the audience. I mean, if someone called him on it or called her on it, I would expect them to clarify that even in the best of cases, only 10% has replicated itself, and that we have no example of the RNA acting as an enzyme carrying out these sorts of functions without associated without associated proteins. I would expect them to say that.
So let's take it this one step forward, because I came to know that proteins, just if you have this peptide chain, it wouldn't be enough. They need to fold and have this 3D structure that has the real properties, and that this protein folding process is such a big deal, and that the folding process itself involves enzymes. So I'm thinking like this: if by a stretch of imagination, I accept that one protein that is beneficial has been created through a random mutation or a series of random mutations, is it rational that we expect that even the enzymes and the other, goes into, whatever, Golgi apparatus or something, to fold it properly, and it will find the right enzymes that will continue the process? Or if it's just a beneficial protein, it will automatically find the proper folding mechanisms. Does this come for free? Is this a free lunch? Or it needs a complete system design? As a chemist, what's your comment on that?
Well, certainly we know today that many enzymes do not fold properly into an active state without chaperones. And those chaperones are other enzymes which help them to fold into the structure they need folding. So there's a paradox there within the field of biology about how these proteins folded. And so there's a lot of study. Protein folding is a big field of study, and how you can get these proteins to fold. There are some proteins that don't particularly need chaperones, that they can go into lipids and fold properly. So some proteins need other proteins to help them fold. Other proteins don't. Other enzymes don't need that sort of assistance. It just depends on the ones that are there. But in order to get them to fold right, it does have to have the backbone sequence to be right. And if you get that backbone sequence wrong, I mean, things start getting mixed up. And especially things that are somewhat near the active site or things that are key to help it to fold. So there's a real problem. It's not just the how it's going to fold. It's how you got those specific amino acids to hook together into the chain originally. Very hard to fathom how that is done. Very hard to think about how that's done without enzymes being able to hook those together. Because without enzymes, you have active side chains on many of the amino acids, and those would participate in the enzymatic coupling in ways that are deleterious to the whole structural backbone. Real problem. And we don't have answers to that. Maybe someday we will, but we just don't have it right now.
So when people talk about, all what you need is a series of point mutations and you have all of those new protein innovations, is it correct to say that this is not a complete representation of reality, completely ignoring other things that you talked about, like those chaperones, like the folding problem, like needing a complete system really to make this thing work?
Yes, you need a complete system. So it has a point mutation, and it's going to start making enzymes from that point mutation. Then you have another point mutation, and another, and another, and another. And then you have to translate that to RNA using enzymes to translate that. So DNA translates to RNA using enzymes. And then that RNA has to translate to the amino acid sequence using enzymes. And then how it's going to get the assistance to have those enzymes fold is unknown in many cases. And so, yeah, I mean, it is a system. Anything you change over here affects what happens over here. And so many times you have to think of concerted lines of evolution. Things cannot happen in isolation. You would have to have several lines of concerted evolution happening all at the same point in time, at the same time, for something to build. And we know that even within evolutionary scenarios, those are slow events that are occurring, but now you have to have many of these coming in all at exactly the same time. It's very hard to fathom. You have to have a lot of faith to be an evolutionist, a lot of faith. I'm not sure I have that much faith.
I think they offer the antithesis of that. They say you just need to believe in science. No faith involved.
It's
right.
faith. It's faith at every step.
It's faith at every step.
Yeah.
Oh, except that there's nothing to have faith about, because there's nothing. So anyway, I'm just worried about time. I wanted to ask you about cell membranes and the proteins there, but I will maybe we'll have another discussion about that. But let me ask you this: Some are giving up on the RNA world hypothesis. So this one was about if cell membranes needed proteins, and where would those come from? And since you need them for the membrane, then you need the proteins in the membrane, and the proteins need the DNA, and then you need the enzymes, and then if you don't have the membrane at the beginning, you don't have a cell. So it's a paradox. So in a nutshell, would you agree that this is a paradox on its own, that you need proteins in the membrane and you cannot have a cell without the membrane? And
absolutely, absolutely. So these things of protocells where they just have a lipid bilayer, which you make by applying shear forces to a lamella. It's not how soap works. Soap does not have a bilayer membrane. Soap has the hydrophilic things on the outside, hydrophobic ones on the inside. The lipid bilayers have hydrophilic, water-loving things both on the inside and the outside, so you have a lipid bilayer. Some people get confused between what a cell has in a lipid bilayer and what soap does to have a monolayer where you have polar on one side, non-polar on the other. But in any case, to have this, it can't just be that you can't just be the lipid bilayer. You have to allow certain things in and certain things out. So you have to have proton gradients. You have to allow certain things in, certain protons out, and this is all controlled by proteins that are opening and closing and controlling all of this. These are highly complex structures. And the other thing is you need enzymes to make the lipid bilayer, because lipid bilayers cannot be symmetrical. They have to be non-symmetric, meaning the outside has to be different than the inside. If you just take lamella and put them under shear, you get some symmetry between the outside and the inside. That would not be suitable for a cell. You have to have asymmetry across this. And the asymmetry right now we know is induced biologically by enzymes called flipase enzymes that flip certain things to the outside and certain ones to the inside.
It just gets more complex as you go, doesn't it?
Yeah. So where are you going to get your lipid bilayer if you don't have the enzymes to do the flipping for you? It's a real problem. And people will say, well, they were much simpler in the beginning and those things just evolved. No, that cannot have been, because you would not have been able to have the proton gradient to have your simple cell. So you cannot keep throwing this right at the feet of evolution and say evolution took care of this, or evolution becomes your God. You throw it at the feet of evolution, evolution took care of it. Well, how is that any different than just making evolution then your God?
This is actually the next question. So I just pursuing this RNA world hypothesis, and it seems that some people are, letting go of it, and they say it wasn't RNA alone, but, peptides and RNA just, evolved side by side, and it's a love story. And they have those drawings. It's not mainstream yet, of course, but does this solve it?
No, because hydrolysis of peptides means the breaking up of peptides is faster than the formation of peptides when you don't have enzymes putting them together. And chemists will say, oh, we do it all the time without enzymes. Yes, because you activated the end of one and you had the other thing protected, and you set it up to do that, and you protected the side chain. How do you do that when you don't have a chemist acting upon it? Nobody knows. Nobody knows. So if you don't have a chemist and you don't have an enzyme, you're hopeless. Is this what you're saying? I mean, it's really hard to do this. And so the hydrolysis rate is going to be faster than the formation rate. And chemists that say, oh, well, these things can happen, we'll dissect their chemistry. This is going to happen. We'll dissect the actual chemistry that they did, and we'll take a look at it. And the nice thing about a real chemist is that when you point something out to them, they'll concede. They'll concede. I mean, because you just can't argue against what's there. And so even the real chemists that are picking on me, it's for very tangential things. They haven't gotten to the heart of anything that I said in that video. Because if they listen to that video, they're going to go, wow, he was right. He was right, over and over again. And those that have contested it, will expose it.